In this video, we're going to take the derivative of general exponential functions. Previously, we looked at the special exponential function e to the x, and we found its derivative was itself e to the x. We looked at the derivative of the logarithmic function, natural logarithmic function ln x, and found its derivative was 1 over x. And we explored a little bit the derivative of 2 to the x, and we are going to find its exact value today. We did do some first principles work with it and found out that the derivative was 2 to the x times some ugly constant like that, and we said, where does that constant come from? What is it exactly? And that's what we're going to work at today. So let's begin then. Let's take a look at y equals 2 to the x, and let's see how we can use these earlier derivatives to help establish the derivative, the exact derivative of this. So I'm going to take the ln of both sides like this, so we can use our world famous down and front rule like that. So we're going to have ln y equals x ln 2. Well, I want you to recognize that ln 2 is just a constant. You can type it in your calculator. Ln of any number you can type in and get values for. Ln 2 happens to be 0.6931. Irrational number keeps going on. So remember that that is just a constant. Let's take the derivative of this one now. The derivative of ln y, according to this, would be 1 over y times the derivative of the argument, and the derivative of y with respect to x is dy over dx. The derivative of x times a constant is just a constant. Much the same way the derivative of y equals 5x, x times a constant, y prime would just be 5. So we have just a constant on this side. We're going to multiply both sides by y so that we can cancel this y off with this y. And you're left with dy over dx equals y times this constant ln 2. Well, earlier in the question, if you remember right from the start, y is equal to 2x. So we'll substitute that in here to get our final derivative, dy over dx equals 2 to the x times some constant, not a nice one, ln 2. So for exponential functions, the general exponential functions, where the base is not e, the derivative is much the same except it's times this constant, and this constant works out to be the ln of the base. So let's look at some simple examples up here, and then we'll work to more complicated ones. So y equals 3 to the x, y equals 5 to the x. The derivative of those is simply going to be y prime equals itself, the exponential function itself, times the ln of the base. And the ln of 3, some constant, a little bit bigger than 1. Y prime would be equal to 5 to the x times ln 5. So in general, we say if the base is not e, y equals b to the x. In fact, it's true if it is e as well. Y prime will equal the exponential function with a given base times the ln of the base. And I say it's also true for e to the x, because y prime equals e to the x times the ln of e, and the ln of e is equal to 1. So now we can look at some more complicated examples and see what we can do with them. So let's consider a product. Y equals x squared times 3 to the x. So y prime will be equal to the first x squared times the derivative of the second, 3 to the x times ln 3, plus the second, 3 to the x times the derivative of the first, 2x. So let's look through this one and see what we can see is a common factor. Y prime equals, I can take an x out, and I can take a 3 to the x out. Taking that out of the first underlined expression, you would get x times ln 3, and I usually write it like that. You could write ln 3 times x if you wanted to, plus 2. So there's an example of a product rule. If the exponent gets complicated, y equals 3 to the exponent x squared, then the derivative will look like this. Y prime equals 3 to the x squared times ln 3, and then times the derivative of the exponent. We would simplify that one to be y prime equals 2 ln 3 times x times 3 to the x squared. So from there, we'll take a look at some more complicated examples. And see how we can make out. So here's a quotient rule question. Y prime equals denominator 5 to the x ln 5 times the derivative of the numerator 3x squared minus numerator x cubed times the derivative of the denominator. Shoot. That was a bad one, folks. Let's see if we can recant our sins here. Y prime equals denominator 5 to the x times the derivative of the numerator 3x squared minus numerator x cubed times the derivative of the denominator all over denominator squared. So y prime equals, looking at the numerator, I see a common factor of x squared times 5 to the x. And when I take that out, I'm left with 3 minus x ln 5 all over 5x, 5 to the exponent x all squared. This one we can cancel with this one, and we're left with y prime equals x squared 3 minus x ln 5 and all over the denominator of 5x. Let's see what happens when we make the exponent more complicated. Y prime equals 5 to the exponent, so notice that doesn't change, times the ln of 5, the ln of the base. Now we're going to multiply it by the derivative of the exponent, 3x squared plus 4. So y prime equals ln 5 times 3x squared plus 4 times 5x cubed plus 4x. Y equals the sine of 2 to the x squared. y prime equals the derivative of sine is cos. And then we have to multiply it by the derivative of the argument. Well, the derivative of 2 to the x squared is itself times the ln of the base times the derivative of the exponent. Let's see if we can organize that a little bit. These are coefficients. These are just numbers that I'm going to put in front. Y prime equals 2 ln 2 times x times 2 to the exponent x squared times cos of 2x squared. In general, when I'm stating the final answer, I try to go from the simple to the more complex. I try to put the coefficient part in front, although sometimes ln 2 I put after x just because I don't want it to look like this. Ln of 2x, it's not the ln of 2x, it's the ln of 2 times x, like that. But that's the general pattern that I follow. Just a couple more examples. Find the tangent at x equals 3. So y prime would be, y would equal 2 to the 3, y would equal 8. So we have an ordered pair of 3 comma 8. We want to find the equation of the tangent line there. That means we've got to take the derivative. Y prime, we get 2 to the x times the ln of 2. At x equals 3, we would get y prime equals 2 to the 3 ln 2. So y prime equals 8 ln 2. That's the slope. Using those two facts right there, we can find the equation of the tangent line by saying y minus y1 equals m onto x minus x1. There's x1 and y1, and there's the slope, m. So y minus 8 equals 8 ln 2 times x minus 3. So y equals, distributing that in, 8 ln 2 times x minus 24 ln 2, and I'll transpose the minus 8 and make it a plus 8. There's the equation of the tangent line. Finally, we'll look at an implicit differentiation question. We'll say something like this. 2 to the x plus 3 to the y equals 3x squared minus 4y. So let's do this one implicitly and see where it takes us. The derivative of the 2 to the x is going to be 2 to the x times the ln of 2, plus the derivative of 3y will be 3 to the y times ln 3 times the derivative of the exponent. And that's going to equal the derivative of 3x squared is 6x minus the derivative of 4y is 4 times the derivative of the exponent, or of the derivative of y with respect to x. Excuse me. So the derivative of 4y is just 4 times the derivative of y, which is dy over dx. So I have two terms with dy over dx in them. I'm going to move them to the left-hand side. 3y on 3 times dy over dx plus 4 dy over dx equals 6x minus 2 to the x times ln 2. Common factoring out a dy over dx. You get 3 to the exponent y ln 3 plus 4 equals 6x minus 2 to the x times ln 2. So dy over dx, our final line, equals 6x minus 2 to the exponent x times ln 2, all divided by 3y times ln 3 plus 4. So that along with a note that I put on Google Classroom should help you with the next set of homework questions, and I'll list those on our Google Classroom stream page. Have a good day.